Hey world, coming back with connected particles topic, and we continue in more harder stuff. I'm going to consider a challenging question for now, and let's have a look. What if three bodies are connected with each other, but the way so that two bodies are staying in the horizontal direction, they moving along the horizontal straight line, while the third body is just moving vertically down, okay? Because it's sort of hanging on the string, and all this string is passing over the pulley. Too many words, it's better to see actually first what we've done so far and then to have a look at the problem itself. So that's useful techniques and approach, general approach and formulas that we use here, okay, for connected particles. We also solved problem one, as you remember, that's EP level, and actually the two ways were shown for you guys by combining two bodies into the whole one big body with the total mass. If we don't care basically about any internal force that do exist in the system, okay. I'll also show you the case where two bodies can be considered separately, and using separation takes a bit more action to go and more steps to go through. But anyway, the final result will be it will be done. So right now we're gonna have a look at this challenging problem. So problem 2 itself actually describes the case where there's three bodies connected with each other so that two bodies stays on the horizontal surface and moving along it, while another object is hanging on the string vertically down and moves down, because definitely if you even take into account the force of friction and any resistant force to the motion, the force due to the gravity for object M1 is greater, and hence the system is moving. Otherwise, it won't move, right? Okay, so that's why we need to start thinking about force body diagram or free body diagram for all three objects. That's the normal step here. Then we will set up the second Newton's law equation, okay, for each object separately, or sometimes maybe we will combine two objects M2 and M3 in a single one if you don't care about tension force that actually exists in between them, okay? If we don't care about those forces, that will be done for convenience and for simplification. And we also need to take into account friction force through the coefficient of friction. So that's why the starting point here is to draw up all the forces, and then I'll show you how the force of friction is connected through with reaction force through the coefficient of friction, which in this case is given as mu, okay? The coefficient of friction between these bodies and the horizontal surface is mu, so you're given here, and you don't worry about that. Okay, so let's draw up all the forces, the x here, and that's why for simplicity I'll depict them with, this kind of stuff, using that purple color. So first of all, for object M1 we do have, of course, the gravity force. Don't mess up with the weight, because it's most of the time it's better to use a gravity force, okay? And in that case it will be always correct. So that's obviously that's going to be the tension force, and let's mark as T1. So this tension force also acts on the object M2. So my idea is to combine both object M3 and M2 in the single one, so we can consider as if there is a total object with the mass M3. So here is the mass M3 plus M2, where we do have tension force T1, okay? But also because we do have the friction force here, so we also apply against the motion, because actually the motion is downward with some acceleration a, and to the right, if we consider horizontal part of the connected particles. So that's why we do have friction here, and That's why the total friction is going to be F friction force that we're going to connect with normal reaction force. Okay, so let's have a look. Now we're gonna set up second Newton's law equation, second Newton's law, and let's write it for object M1. Due to the fact that they obviously can be considered as connected particles. As you remember the previous case, we discussed that there are two different types of straight lines. One is horizontal one and the vertical one. And we understand that this string is inextensible and it's weightless. So we are going to consider as the whole object moves with the same acceleration at given point of time. I mean, each part of this system is moving with the same acceleration and magnitude. However, acceleration in direction is going to be different, of course. All right, so for M1, we can set up M1A is going to be equal to M1G minus T1. Okay, as you understand, I've chosen the positive direction downwards. So set up this direction downwards as a positive one. So maybe it's better to say this one. So let's say that's positive y direction. And let's say positive x direction is going to be in that way. Maybe proper to set up this arrow here. And it's going to be positive x direction. As you can see, sometimes, you can use the Cartesian plane and set up the xy axis like as you normally do it for graphs, right, in algebra and math. But you can find more appropriate to use separate axes. This also works, and it doesn't matter. So in that case, I'll choose this way as the most appropriate. Okay, so for the object which basically combine two masses M2 and M3, we do have the following. So the total mass M2 plus M3 times acceleration is going to be equal to, of course, to the right, here is the tension force due to the fact that this M1 pulls all the system along the way, and minus friction force. So right now, we need to find what? Find the expression for the magnitude of acceleration A and for the tension of the thread. Okay, so first of all, let's set up a friction force. As you remember, it's proportional. So this, there are two types of friction force, dynamic and static friction. So in our case, all is moving, and we can set up the proper equation for the friction force of dynamic friction force. So in that case, it's proportional to the reaction force. So that's why we can write mu times r, where r is the total force that acts upwards. Okay, so it's going to be upwards, and let it be r here. So in vertical way, there is another force, m2 and m3 times g, which is going to be gravity force. So that's why, due to the fact there are no other force, we can say that the reaction force is exactly represented by the gravity force for the combined object. So that's why the friction force in that case is going to be equal mu g in the total mass. All right, so it's done with the friction force, and now we just come back to the equation. So here we're going to add two equations in order to get rid of T, tension force. So that's why we'll get A times, so I factorize A on the left side, and that's going to be the total mass, M1, M2, and M3. Okay, and on the right side, T1 will be cancelled everywhere, and there will be M1G minus what you have here, mu g, and the total mass m2 plus m3, because instead of friction force we plugged this expression. So I just even set up the frame so that you understand how this works. and also that one, okay? And basically we've add up two equations, 1 and 2, all right? So and finally what's left is to express acceleration from here. That won't be like hard stuff. It's gonna be pretty easy. And we can do the following. So what I'm gonna do, I'm just going to factorize g and write that over the total mass m1 plus m2 and plus m3 in times g. And that's going to be the resultant formula for the acceleration that each part of the system has in that case. So let's analyze. Let's assume that there is no friction. Let's just consider and provide some more, deeper analysis here. If mu is going to be 0, means no friction, no friction here, okay? We understand that we will get basically acceleration to be equal a portion where m1 represent in total mass. I'll mark a total mass of the system as m total. So that's going to be a fraction m1 to the m total, okay? As you understand here, m1 is the mass of the hanging object that actually, due to the gravity, pulls the rest part of the system. And obviously, the gravity force, it was falling if you actually cut off this string. So if you cut off the string like here, okay, your object will be falling with acceleration g. However, due to the fact that it has the rest system, basically the carriage behind it, it's not falling freely, but it falls with acceleration proportional to, of course, acceleration of free fall with coefficient m1 to m total. Let's assume that all masses are equal. So in our case, A is going to be a 1/3, right, of the G. Pretty natural explanation for that. This is analysis as if no friction. But in case of the friction, of course, acceleration is going to be smaller because by subtracting mu times the total mass m2 and m3, you basically diminish the value of numerator and hence diminishing acceleration, total acceleration of the system. All right, so I hope you got it. That was a brief analysis. What if? What if we assume that there is no friction in the system, not only in the pulley, but in the whole system, but that with friction. This formula is given with friction, okay? Friction. Okay, and the rest part, what's left is to express tension force. But where? Find expression for the tension of the thread binding together bodies M2 and M3. So right now, of course, we need to apply the tension force. The tension force to each object. So that's why, to answer the second part of the question, I'll just move here. And now we ask about this tension in this thread, okay? Connected or binding M3 and M2. So basically, right now, we can say that because we know acceleration A, we can basically complete an equation for either for M2 or for M3. So let's complete for M3 because it would be much more convenient. Let's be tension going to be T2. So we do have still the same friction force, but in that case, friction force is going to be like kind of, let's say 3, because this friction force, F3, is going to be proportional to the reaction force for the object, for the only M3. So that's why we can put R3 over there, which of course is going to be equal to the gravity force M3G. So that's why we can write the same coefficient of friction and we times the gravity force. And that's only what amendments we need to set up for our object. So that's why we can set up the same second Newton's law for M3, providing that we do have a positive direction in that way. So the same x-axis here. And we'll set up the second Newton's law. M3 times A, acceleration, is going to be equal to tension force that we're looking for and minus friction force, which in our case is going to be mu times M3 and G, from where we can find the tension force, which is going to be M3, and in the brackets we'll get the sum of A and mu G in that case. If we plug expression for the acceleration, so acceleration is equal to, so one more time, m1 minus mu, the sum of m2 and m3 times g and divided by the total mass. We'll get another expression for T2 when we plug in. Okay, so just write down here and we plug this acceleration here. So that's why we can even more take out g as the common factor, and we'll be left with m1 minus mu m2 plus m3 and plus mu times the total mass, so m total. Okay, m total, where m total is this one, so that's going to be the total mass, mt, total mass, and we divide everything by the total denominator m1, or common denominator m1, m2, and m3. And now just what's left is to just simplify the expression. So that's why the final expression for the tension force, so mu m2 and m3 will be cancelled partially with that one, because if we start expanding the brackets, we'll cancel this part, and that's why we'll be left with the following: m3g times what will be on top is simply m1 1 minus mu. I just skip maybe some steps of simplification to save you time, and you can try to do by your own. And the total denominator or common denominator still stays the same. Okay, and that's going to be the final expression for tension force, that basically here in the thread connecting m2 and m3. So that's why it was challenge problem for A level. It's not really hard, but you know, it takes more steps and more general steps. Basically, it's based on how well you can derive the formula, okay, and how well you can solve a system of equations. So I hope everything is correct here, if I haven't messed up something, but I think it's more or less what I'm expected to have. Okay, so except for yeah, I guess plus mu. Yeah, when I factorize m1, yeah, simply we'll be left with mu m1 here, so mu m1 here. Okay, and the rest part will be cancelled, so that's why 1 plus mu. Okay, and again, as you understand, if, let's analyze a bit more, if mu is going to be equal to 0, so no friction, what will happen with the tension force? T2 is going to be equal to m3g times the coefficient m1, basically the weight or the fraction or the share which m1 is represented in the total mass. So that's why it's going to be m1 plus m2 plus m3. All right, so if there is no friction, that's going to be the result. And again, it's more or less sort of, you know, pretty obvious outcome in that case. Okay, so that's the ways you can solve this problem, and I think you should got it. You should got this technique. So if you went through problem 1, problem 2, and similar type of questions, I think you will be able to solve exam style questions and you won't have any problems. Hope you like that. That was Daniel Dallas, and see you in the next episode. Peace out.